Welcome back. Today, we're going to get our hands dirty on the digital assembly line. But instead of building a car, we're building an AI, bolting it together piece by piece. The goal? To construct a neural network that doesn't just process numbers. We're going to teach it how to actually see.
So, here's our game plan. First, we'll start with the basic framework. Then, we'll install the most important part, the vision system. After that, we'll do some fine-tuning, add a few critical safety features, and finally, we'll see how our new, souped-up AI actually performs.
Okay, every big project starts with a foundation. For us, that's a simple deep neural network made of what are called dense layers. It's our starting point, but you'll see pretty quickly it's got a major flaw.
So let's look at a key part of this initial design. See that flattened layer? What it does is kind of brutal. It takes a perfectly good 32 by 32 pixel image and just stretches it out into one single long line of over 3,000 numbers. It's like taking a photograph and putting it through a paper shredder.
And right there, that's the fatal flaw. By doing this, the network completely loses the image's structure. It has no clue which pixels used to be neighbors. A pixel for an eye and a pixel for a nose. To the network, they're just two random numbers in a giant list. All that context is just gone.
So that's our first big problem on the assembly line, right? How can we ever expect this thing to recognize, say, a car if it can't even tell that the wheels are at the bottom and the roof is at the top? We need a better part. We need a serious upgrade.
And that upgrade is a game changer. We're about to install a highly specialized component, the absolute core of how computers see today, the convolutional layer. This is where the magic happens.
So what is this thing? Well, you can think of the convolutional layer as a toolkit full of tiny, specialized magnifying glasses. We call them filters. Each filter has only one job, to slide across the image looking for one very specific thing, like a sharp vertical edge, a gentle curve, or maybe a patch of blue that looks like the sky. And here's how it actually works, deep down. That filter, which is really just a small grid of numbers, lays on top of a patch of the image. It multiplies its numbers with the pixel values underneath and adds it all up. If the patch of the image is a great match for what the filter is looking for, you get a really high number. If it's a bad match, you get a low one. It's basically a feature detector. Just look at this in action. We've got two different filters here. One of them is built to spot horizontal lines, so you can see how it lights up on the top and bottom of the cup. The other one? It's on the hunt for vertical lines. Now, the truly amazing part is that we don't have to handcraft these. The network learns thousands of them all by itself during training. It literally teaches itself to be an expert at spotting all the little details that make up our visual world.
All right, we've got the vision system installed. Now it's time to pop the hood and do some tuning. We have two key dials we can turn to really dial in the performance: strides and padding.
So, on one hand, you've got strides. This is basically the step size our little filter takes as it scans the image. A small stride means it's very meticulous, looking at everything. A bigger stride lets it jump across the image, which is faster and makes the output smaller. And then you have padding. This is a simple but brilliant trick. We just add a border of zeros around the image. Why? So our filter can properly see the pixels right at the very edge.
And here you can see that padding idea perfectly. By adding that border of zeros, the filter can actually hang off the edge of the original image. That means the corners and edges get the same amount of attention as the center, and we don't lose precious information. It's a neat little trick. Okay, so here's a look at our assembly so far. The image comes in on the left, goes through a couple of our new convolutional layers, and notice what's happening? The image gets physically smaller, but it gets deeper with more and more channels. You can imagine each new channel is like a transparent sheet laid over the image, where one sheet highlights all the vertical lines, another highlights all the circles, and so on. The network is building up a really rich, complex understanding of what it's seeing. We've built a really powerful engine. But, if you put a huge engine in a car with no suspension or steering control, you're going to crash. For a neural network, that crash is called overfitting, where it just memorizes the data instead of actually learning. So, we need to install some stability controls. The first control system is called batch normalization. As the network learns, the numbers flowing between layers can go absolutely wild, making it super unstable. Batch norm is like a regulator that steps in after every layer and just calms things down, rescaling the numbers to a sensible range. Think of it like putting shock absorbers between each part of our assembly.
Our second tool is even more interesting. It's called dropout. And here's the crazy idea. For every single step of training, we just randomly turn off a bunch of our neurons. Just zero them out. This forces the other neurons to pick up the slack and learn the same information, which builds redundancy. It stops the network from getting lazy and relying on just one specific neuron to do all the work. It makes the whole system tougher.
So, these two things, batch normalization and dropout, they're like the quality control supervisors on our assembly line. They keep the whole process stable and honest, and they make sure our network is actually learning to generalize, not just cheating by memorizing the test.
All right, the last bolt has been tightened. We've taken our simple starter model, ripped out the bad parts, installed a sophisticated vision system, tuned it up, and added stability controls. It's time to roll it off the assembly line and see what this thing can actually do.
And here she is, our final model. It looks a lot more complex, doesn't it? A whole stack of those new layers we added. But here's the part that's really going to surprise you. Look at the total number of parameters at the bottom. That's how many internal knobs the network has to tune. It's about 592,000. Now remember our first simple model? That one had over 646,000. So get this, by using smarter components, we've built a more powerful network that is actually smaller and more efficient. That is just fantastic engineering.
And here it is, the moment of truth, the payoff. Our original simple model, it was only 49% accurate, basically a coin flip. Our new, smarter, convolutional model, it hit 71.5% accuracy. That is a huge jump in performance, and it all came from just building it better.
And this is what that number actually looks like. It's not just a score on a chart. Our network is now correctly identifying dogs, frogs, trucks, ships. It's really seeing what's in these images. We did it. We taught it how to see.
This quote from the source material just says it all, doesn't it? The secret wasn't to make it bigger. It was to make it smarter. The right architecture, the right components, that's so much more important than just blindly adding more horsepower.
You know, everything we've done today, our entire assembly line, has been about one thing: deconstruction, taking a complex image and breaking it down into simple, understandable features. But what if we ran the assembly line in reverse? Well, there are layers for that. This one, a convolutional transpose, does the exact opposite. It takes simple features and intelligently builds them back up into a bigger, more complex image.
And that's the thought I want to leave you with. We've just successfully built an AI that can take an image apart to understand it. But what happens when we give it the tools to put those pieces back together again, from scratch?